Good morning, fellow mathematicians. Welcome back to another video. Back with some, you could say, number theory, I guess. We're going to prove today that if we take some n element of natural numbers, well, this number can be either odd or even, meaning that it can be odd and even at the same time. And I'm going to provide you with two little proofs today, and after we are done with those proofs, this gives us a chance to create a partition of natural numbers into exactly the set of even and odd natural numbers. If you don't know what a partition is, take a look at my, well, set theory video, Introduction to Sets and Operations video. Link in the description probably. We are going to dive right in. So the first proof is just a simple proof by contradiction. So before getting really started, we have to rephrase this right here a little bit, this little statement. So this right here is equivalent to saying that for all n element of natural numbers, well, we have that n is either 2 times k, where k is element out of natural numbers. By the way, we want to take n as the set in the sense that 0 is included. 0, 1, 2, 3, 4, up until, I don't know, the biggest natural number. God bless Ababu, Mohammed, my boy. Okay, so k is element of natural numbers. Or, well, n is of the form 2 times k plus 1, where k is element of natural numbers. Okay, with that out of the way, we have written this in a more mathematical way. And now we can start using proof by contradiction, meaning this statement right here is going to be negated, and then we are going to find a little contradiction in this opposite statement in order for this original statement to be true. So, what's the opposite of this statement? Well, the opposite, let's assume that there is some n element of natural numbers, well, such that n is equal to 2 times k and n is equal to 2 times k plus 1. Or instead of k, let us use p, for example. I really don't care. With p also being out of the natural numbers in this case. Well, the cool thing is, we have this AND operator at the moment, meaning this and that is equal, and since equals 2 is an equivalence relation, it's also transitive, and that means that 2 times k is equal to 2 times p plus 1 at the moment. So that's equivalent to saying that 2 times k is equal to 2 times p plus 1 at the moment. Okay, what next? Well, 2 is not equal to 0, so that means we can divide both sides by 2. You can take a look in the piano axioms and see that 2 is just a successor of 1, making it not equal to 0. Coolio! So that also means that's equivalent to saying, well, 2 times k over 2 is just k, equals to 2 times p plus 1 over 2. We can break up this fraction into 2 times p over 2 is just p plus 1/2. Well, you see, on the one hand, we have assumed that k is element of natural numbers, so this right here is element of natural numbers. But on this side, well, p is element of the natural numbers, but 1/2 is element of the rational numbers right now. Those two added together is not element of natural numbers anymore. So this thing right here is element of the rational numbers, but without the set of, well, natural numbers. Just meaning, that's a contradiction in itself. We say that this thing, for example, here is 3, being equal to 1/2, for example. Doesn't work out, my boys, doesn't work out. So this right here in itself is a contradiction, meaning that our original statement is indeed true. We have proven this to be correct, and now for the second proof. The next proof is going to make use of the principle of mathematical induction. For this, we need to have a little proposition. We want to prove to be true for all natural numbers, an element of the natural numbers. Well, I've just said this thing equal to our proposition, you could say, p of n, right here. And what we want to do basically, we want to prove this statement to be true for the least element of natural numbers, 0, right now. And then we want to say that this statement is true for some m, some random natural number in between. And we want to see if this proposition p of m ensures p of the successor of m to be true in the end. It's like a domino effect, you could say. It just holds for all natural numbers then. Okay, let's start off with p of 0, you could say. So, p of 0, what is that? Well, 0 is nothing but 2 times 0. And by definition, that's of the form 2 times k out of natural numbers, making it element of the even natural numbers. Cool! Hey, we have done that. And now we want to assume that p of m is true. So, what does it mean for p of m to be true? Well, that means that this natural number m is either odd or even, not both at the same time, by our proposition. We are assuming this to be true, and now let's take a look at p of successor of m. Successor of m just being m plus 1, you could say. P of successor of m is equal to p of m plus 1. Now we have to consider two main cases, basically. Either m has been odd or m has been even. Let's start off with the even one. So we have case 1. M is element of the even natural numbers. Well, what does that mean then for our m plus 1? Well, if we have m plus 1 now, well, m is element of the even natural numbers, meaning it's of the form 2 times k, where k is element of natural numbers, and now plus 1. And by definition, this right here is just an odd natural number. So, that statement is already good. And now for the second case, let's see if the second case turns out differently. It doesn't. Case 2. So, m can be element of the odd natural numbers. Well, then for m plus 1, what do we get? Well, m is now by definition of the form 2 times k plus 1. And also adding a 1 to it. But what is 1 plus 1? Well, that's just the successor of 1 in this case, being 2 as a little shortcut. So we have 2 times k plus 2 now. And now we can just make use of the left distributivity, or what a fucking stupid word. We can make use of the left distributivity on the natural numbers to factor out this 2. 2 times k plus 1. Well, k is element of natural numbers. This right here is just a successor of k, being element of natural numbers. 2 times something out of natural numbers is element of the even natural numbers. By assuming that p of m is true, we have shown that p of the successor of m is also true for all m element of natural numbers, proving this statement right here to be correct. There was not too much work, it was okay. But the cool thing is, we can create a partition now. Because you see, and or are just equivalent to something else. Intersection and our union in set theoretical terms, you could say. Let's take a look at that. So, we want to create a partition of the natural numbers, which is as follows. Well, we have just the even natural numbers and the odd natural numbers. And what we have shown now by this right here is that the even natural numbers intersected with the odd natural numbers is just the empty set. How can we rewrite this? Well, that just means that there is no n out of the natural numbers such that, well, n is odd and even at the same time. N is equal to 2 times k, and n is equal to 2 times k plus 1, where k is element out of natural numbers. Well, that's just what it says, you see? And this intersection, kind of equivalent. That's a partition, so that means if we take the union of those two sets, we are going to end up with the set itself. So, NE in union with NO is indeed going to give us the natural numbers, because we have shown by induction that this is the case right here. For all natural numbers, it's just that they are either odd or even, not both at the same time. Meaning, this is just some n out of natural numbers, such that n is equal to 2 times k, or n is equal to 2 times k plus 1, where k is out of natural numbers once again. Yeah, and that's basically it. So with this right here, we have also shown that there exists a partition of natural numbers, such like this. I thank you guys for watching. If you did enjoy this video, please like and subscribe and recommend the channel if you have ways to do so. To your mom, to your sister, your dog, whatsoever. And well, you can support the channel by buying those t-shirts or support the channel on Patreon, or don't if you just wanna take a chill little look into some videos. And up until the next video, have a flammable day. See ya!